start with the scenario. Oliver ordered some blocks. The blocks are here. Oliver wants to make some tables and chairs using them. Mr. William, the retailer, who is ready to buy the tables and chairs using them. Now, Oliver, being a calculating guy, finds that selling a table to Mr. William would give him a profit of rupees 300 and selling a chair would give him a profit of rupees 150. But the thing is that the stuff he has with him is limited. He has 14 large blocks and 18 small ones. He finds out that for each table he needs 2 large and 2 small bricks, and for each chair he needs 1 large and 2 small blocks. Now, more profit on a table makes him a bit biased, and he decided to make only the table out of all the bricks he has. And by the time the 7th table is completed, the large blocks are over and he is left with 4 small blocks unused, with each table giving him a profit of rupees 300. So now his total profit in this case would be rupees 2100. Do you think he made the optimal use of his blocks? Do you think this is the maximum profit he can make? How do you make sure if it is the right way or not? Well, that's what we learn here in this video. Optimization problem. About this we'll be going to discuss in this video. In these problems, we will maximize and minimize the function, keeping in mind some conditions that are specific to the situation at hand. Minimizing cost and maximizing profit are source examples of an optimization problem. The example which we discussed just now was an optimization problem in itself. And there we were optimizing our profits on the sale of tables and chairs. Let's discuss some terminology related to such problems, which we will be using throughout our video. First one, objective function. In the above illustration just we discussed, let's say I sell X tables and Y chairs. Given that selling a table will give you a profit of rupees 300 and selling a chair will profit you rupees 150. Now, my total profit would be 300x plus 150y. Now, I have to maximize this function. The linear function z is equal to ax plus by, where a and b are constants that need to be maximized or minimized is known as the linear objective function. Now, what are constraints? What will be the maximum value of 300x plus 150y? You keep on increasing x and y and the value of the function just keeps on increasing. So this gives an impression that there is no maximum value for this function. But if you carefully observe the above problem statement, then you will have a limited number of Legos. And hence you can only have a limited number of chairs and tables built. You cannot increase the values of x and y beyond a certain limit. Constraints on linear programming problems are the conditions that restrict the values of x and y independently or dependently. Please note that the independent variables x and y constituting the objective function are called decision variables. Linear programming problems are optimization problems where the objective function and the constraints are linear functions of x and y. Example which we were discussing is a linear programming example. See the objective function, that is 300x plus 150y, which is a linear function. And again the constraint, this is again a linear function of x and y. Now the graphical method is required for solving the linear programming problems in two unknown. The first step, to graph the feasible region. Now the obvious question is, what is the feasible region? You have a few constraints with you in the form of inequalities. Say x greater than or equal to 0, x less than or equal to 0, y greater than or equal to 0, like that. And each inequality defines some region in the xy plane. Now, the feasible region is the region that is common to all the constraints of the given optimization problem. The set of values of the variable x and y which satisfy all the constraints and also the non-negative conditions is called the feasible solution of the linear programming problem. That is, all the values lying on or inside a feasible region is the feasible solution. You should also note that the feasible solution is different from that of the optimal solution. There may be infinitely many feasible solutions as there may be infinitely many points satisfying all the constraints. Now, what is the second step? The second step is to determine the optimal solution from the feasible region. The optimal solution is one or more of the points lying in the feasible region. That is, those points of the feasible region that gives optimal value are called as the optimal solution and they lies in the feasible region. Now, since the two variables are positive, we consider only the first quadrant. For example, x greater than or equal to 0. So, already plotted here. This will be y greater than or equal to 0. You can also see each constraint is of the form ax plus by greater than or equal to c or maybe ax plus by less than or equal to c. Here it is shown ax plus by greater than or equal to c. Each constraint line divides the first quadrant into two regions, say R1, R2. For each constraint, shade the region which satisfies it. Right? Now, take any point in any of the two regions. Let's say you take a point in R1. Substitute the point in the constraint you are identifying the region for. Now, if the point satisfies the inequality, then shade R1. Else, shade region 2. Now, corresponding to each constraint, we have obtained a shaded region. And the intersection of all these shaded regions will give you the feasible region of the linear programming problem. Now, how to determine the optimal solution out of all these feasible solutions? And these two theorems will take you there. The first theorem, let R be the feasible region for a linear programming problem and let Z is equal to Ax plus By being the objective function. Then, the first theorem states that Z has an optimal value, that is either can be maximum or a minimum value, where the variables x and y are the constraints defined by the linear inequalities. Also, the optimal value must exist at the corner point of the feasible region. Now, you may get a question, what is this corner point? Corner point is the point of intersection of any two boundary lines of the feasible region. For finding the maximum value, you choose the corner points at which the value of the objective function went to a maximum possible value. And for the minimum value, you need to choose the corner point in such a way that the value of the objective function will be minimum. Now, here comes the theorem number 2. The theorem 2 states that if R is bounded, then the objective function Z has both a maximum and a minimum value on R, and each of these occurs at a corner point of the region. So, all of you have to remember one thing. If the maximum or minimum value of the objective function exists, it will exist at a corner point of the feasible region only and nowhere else. And if the feasible region is unbounded, then the minimum or maximum value for the objective function may or may not exist. But if it exists, it will exist at the corner point itself. This we have to remember. Let us do it for the problems. Solve the following LPP graphically. The question is, maximize z is equal to x plus 2y. Subject to the constraints are given: x plus 2y greater than or equal to 0, 2x minus y less than or equal to 0, 2x plus y less than or equal to 200, and x and y both are greater than or equal to 0. Let's see the solution. To maximize z is equal to x plus 2y subject to the constraints xy greater than or equal to 0, x plus 2y greater than or equal to 100, first we have to plot x plus 2y greater than or equal to 0, and it's shown here, x plus 2y greater than or equal to 0. Now second, we have to plot for 2x minus y less than or equal to 0. Now the third constraint, 2x plus y less than or equal to 200. On plotting the graph of the equations, we observe that the shaded portion is the feasible solution, right? Now, feasible region is the intersection of the shaded portion, which we have seen just now in the graph. Now, the possible points for maximum Z are A 20, 40, B 50, 100, C 0, 200, and D 0, 50. Now, where this value of Z is maximum, we need to find it. We have to substitute in this and we have to find the maximum value. And you can find, we got Z is equal to 400 corresponding to C, that is 0, 200, right? So, the Z is maximum at point C 0, 200, where the value of x is equal to 0 and value of y is equal to 200. Shall we be able to solve the diet problems using linear programming? Let's find out in the upcoming video. Now, let's have a quick recap.
Manorama Horizon. Learning made simple.